Um, like I said, I had been ill for a while, and so things just did not move as I had planned. For now, what I'm going to do is I'm going to go quickly through like 3 topics, even 4. Um, we can take some time to do a review in the future if you want. But I just need a promise that when I post the invitation that students will come. Because we missed 2 sessions during which I logged in and nobody was here. And then, of course, I became ill, and so we missed another 2 sessions. So we are way behind, and we cannot, um, like drag ourselves behind. So let's see if we can do our best. And then I'm going to also now grade the homework assignments. I was hoping that I could review some of your assignments with you, and so that students who have done it wrong could resubmit. Nobody took me up on that offer. And so I'm just going to grade the papers as they are. But I'll provide an opportunity either for a revision or for some extra credit or something like that. I'll see what I can do. Now, the stage at which we are is really where we get into, we've done descriptive statistics, and then we have to get into probability distributions, and then from probability distributions, we get into inferential statistics, which will be based on continuous normal distribution. Okay. Now, when we are doing statistics, one of the basis of what we call inferential statistics is understanding of probability distributions. And so I'm going to basically look at a probability distribution and see where we take it from there. Okay, so for now, I'm going to pause the recording so I can get something on probability distribution. So in a very simple way, what is a probability distribution? And I'm going to go through it quite quickly so that we can move on. I will share screen. Okay, what happens in doing statistical analysis, or what happens in nature, is that certain values of a variable, differ, okay? In the sense that a variable would have different sets of values, okay? Different sets of values. For example, I have an example up here about claims. Let us say insurance claims. Claims about non-deliverance of a promise, okay? For example, claims of damage. So let us say that customers who purchase goods come and claim damage on some of the goods that um, uh, they buy, okay? And we take a number of days, okay? Here, we're looking at claims on policies, okay? And so we look at, say, 94 days. There are 94 days that we are looking at. During those 94 days, for example, there was 21 days when there were no claims. Then there was 18 days when there was 1 claim. There are 16 days when there are 2 claims, and so forth and so on. Now, that is a frequency distribution of claims. Now, we can translate those frequency distributions into what we call relative frequency distributions, which we have discussed already in earlier sessions. Now, those relative frequency distributions is what we call a probability of occurrence. For example, what is the probability that there will be no claim on a particular day? What is the probability that there will be 1 claim on a particular day? Now, the probability of a particular value of a variable is simply the percentage of times that that particular variable occurs. And so here, for example, the probability of no claim is 22%, which is actually 21 policies or 21 days which there was no claim divided by the total number of days that you are looking at. Okay. And so you have a probability distribution. Now, we can use this probability distribution to create what we call an expected value, an expected number of claims. Okay. We can use this probability distribution to create an expected number of claims. Okay. Now, this is the same problem. Okay. Now, what is the expected value? As an expected number of claims, or what you in statistics is an average. Expected value is an average. Okay. And so what is the expected average number of claims? And the expected number of claims mu, or expected value of the number of claims, is the summation of each value times the probability of that value. And you sum that probability, which is what we have done here. The summation of x times the probability of x. For example, 0, and the probability of x occurring is 22.34%. And so x times p of x is 0. Okay. And so we also then take the value one claim, times probability of one claim, which is 19.15 and 0.19. And when we sum x times the probability of x over the number of possible values, we see that there's an expectation of between 2 and 3 claims over a 90-day period. Okay, and say it's 2.33. So there's everywhere from possibility of 2 and 3 claims, but we say 2.33. So that is an expected value. Now I'm going to use this to address one of your homework assignments. Okay, so I'm going to stop share this. This is one of your homework assignments. Okay. This is one of your homework assignments. This is a frequency distribution of the speeds of a sample of cars along a segment of roads shown below. Okay. Okay. So I'm going to use this, I said, use this table to prepare a relative frequency distribution of car speeds along this segment of road. Okay. If cars that exceed 65 mph are issued tickets, what percentage of cars will receive tickets next year? Okay. If the average ticket is $85 and it's expected that 320 cars will pass this road next year, how many cars are expected, okay, to receive tickets, and hence estimate the state's revenue from this segment of road? Okay. So what is the expected number of cars? Okay. So if the average ticket is $85 and it's expected that 320 cars will um, pass through this road. Okay, so we can use this to calculate, say, the expected average speed. Okay. Right. So I'm going to use this to um, create a frequency distribution. I'm going to copy this. I'm going to stop share that, and I will pull up. Share this.
Hello, Professor.
Hello?
Yes. Would you be posting this recording?
Yes, I will.
Okay. Just because I have class now at 6 and I have to leave.
Okay. All right. So what I'm going to do is I'm going to use this. I can see the speeds. Let me see what's going on here. The speeds are in ranges, so I'm going to create a range here, um, a midpoint, 45 to 55. The midpoint is 50, 55 to 65. The midpoint is 60, 65 to 75. The midpoint is 70, 75 to 85, and the midpoint is 80. Okay. All right. And so what is the expectation? What is the probability distribution? P of X. Okay. Now, how many cars did we observe? We um, observed 375 cars. So the probability of cars within the range 45 to 50 equal G5 over dollar V dollar 9. Sorry, what's the F5? 5 over dollar F dollar 9. Okay, which is 0.4. Now we drag this down. So dollar F dollar 9. Okay. All right. So that is the relative frequency distribution, the probability of X, okay? So now, what is the expectation? What is the expected average speed? Okay, the expected average speed, so E of X, that is the expected average speed will be P X times P of X, okay? X times P of X, which is equals H5 G5. There, and you go down. So the expected average speed will be equal so the expected average speed on this road is 60.5. Okay. So if you wanted to answer what is the expected average speed of cars here? Okay. So that leads us to expectations. Now, so this is how we calculate the expectation of the speeds of the average speed of cars on this road. Now, what we have done here is what we call discrete probability distribution, okay? In order to move to the next topic, which is inferential statistics, we have to now talk about continuous distribution as opposed to discrete distribution. The discrete distribution here is, now I'm going to stop sharing to better illustrate what we'll call a discrete distribution. Okay. What do we mean by discrete distribution? Discrete distribution is such that the values of a variable have discrete values. So between any two values, you do not have any other value. For example, you have 0 claims, and then you have 1 claim during a period, okay? During this period of 90 days, let us say we have 18 periods when there's only 1 claim, okay? So now when it comes to think about it, and what we'll call this discrete distribution. So discrete distribution, because between 0 and 1, there is no other value. Between 1 and 2, there is no other value, okay? For example, you cannot have 1.5 claims or 1.5 claims on 1.00001 claims. No, it's either 1 claim or 2 claims, okay? It's either 2 claims or 3 claims. There cannot be 2.5 claims. So we'll call these kinds of values discrete values. But these are not the values that we use when we are doing inferential statistics. We use what we call continuous values, and the probability distribution for continuous values are called continuous probability distributions as opposed to discrete probability distribution. The probability distribution that we are seeing here is a discrete probability distribution, not a continuous distribution. Okay. Now, so I'm going to go from this to continuous probability distribution. Like I said, I'm going to go through a couple of topics. But I would like us to come back next time and do some examples on continuous distribution. But I'm going to illustrate uh, the beginning of continuous probability distribution.
Codes.
Now go back to what you were saying. Let me take it from the beginning.
Yes.
These are some
So
questions about the hypothesis testing. Okay.
yes. Towards the bottom of the assignment, there are some codes for some shift when code or location code.
Okay.
What does that mean?
Okay. This is why I said I would like to focus on that in the next lecture.
Okay.
Then I'm going to just talk about the meaning of continuous distribution, and we're going to use normal probability distribution. But let me answer your question though. It's a location code, okay? We
Right.
are looking, what you are looking at, which we will talk about next month. I'm going to focus on this assignment next time because this is my purpose. My purpose is to do these examples for you, and I'll do one, and then you all can do the rest, okay? But,
Okay.
okay. What we're looking at in your problem, and I'm glad you brought this question up, okay? This is the purpose of these office hours. What we're looking at there is, for example, you have a workshop, okay, or a manufacturing facility, right? You get
Right.
that? Okay. Now this company has 3 locations. Okay, one in Brooklyn, one in Queens, one in Staten Island. So the location code 1 will refer to, say, Brooklyn code, Brooklyn location. And location code 2 will be Queens, and location code 3 will be Staten Island. And the whole purpose of that assignment is to compare the activities in those 3 locations through a hypothesis test. And a hypothesis test, is a comparison to say whether there is any difference in the number of claims between Staten Island and Queens, and between Staten Island and Brooklyn, and between Queens and Brooklyn. So that was the purpose of that assignment. And we're going to spend time talking about it next time. But for today, let us lay the foundation for understanding those kinds of problems. You follow me?
On you? Yes.
Okay. All right. So what I'm going to do is I'm going to pull up uh, an example of what we call a continuous distribution. Okay, like we said, in a discrete distribution, there are between any 2 values, there is no other value. Okay, for example, there are 18 periods when there was only 1 claim, and there are 15 periods when there's 2 claims. Okay, so the whole idea then is that there is no such thing as 1.5 claims or 1.0000001 claims. But when you have continuous variable, you can have an infinity of possible values between any 2 values. For example, an egg would weigh 2 ounces, but the next one will weigh 2.000000001 ounces, which makes it different from the other one. Okay, so that kind of a measurement can be. Okay, if somebody was born and their age today is exactly 2 years, the person who was born 1 minute after that person is 1.9999999 years. So compared to the person who is exactly 2 years today. So age can be a continuous value. The weight of an egg could be a continuous value. Okay, so now the probability distribution that describes values that are continuous are called continuous probability distribution. And there are many continuous probability distributions. The one that we use very often in statistical analysis is called the normal distribution. Okay, it's called the normal distribution. I'm going to put up an example of the normal distribution and what it looks like. Okay, that is a normal probability distribution, as you can see. A normal probability distribution is illustrated in the diagram above this table. And the normal probability distribution is a hypothetical distribution, and it has a value, it has a mean value and a standard deviation. The mean value of a standard normal distribution is 0. It has a mean of 0, and it has a standard deviation of 1. You can see that the normal probability distribution looks like a curve. It is a symmetrical curve. And the mean value, 0, occurs exactly in the middle of the normal distribution, okay? And so if you go one standard deviation to the right of the mean, or one standard deviation to the left of the mean, you are going to have the area of the curve will be 0.3413. As you can see here, I am pointing at it, okay? So any number of steps to the right, or any number of steps to the left will have an equal area under the curve. And so the probability that you can have any values between any two values is measured by the area of the curve under that value, okay? So the area of the curve between 0 and 1 is 0.3413. As you can see, I am pointing at it. Are you seeing my screen? Hello?
I'm here, Professor. I'm listening.
Are you seeing my screen?
Yes, I am. I'm seeing the chart here.
Okay, so you can see what I'm pointing at.
Yes. So that would be 0.313.
3413.
Yeah.
Okay.
It's 34%.
Yeah. So whether you are going to the right, okay, if you go from 0 to the right, one standard deviation, the area under the curve will be 0.3413. And if you are going from 0 to the left of the curve, one standard deviation, the area of the curve is also 0.3413. Okay? Now, this is how we measure probability. What is the probability that the value Z, which measures the probability any number of steps under the curve? What is the probability that we are what is the probability that we are two steps to the right, between 0 and 2 steps to the right? Okay, the probability is the probability is 0.475, or because probability can only be less than 1. Okay, so what is the probability that we're going to be like 2 steps to the right of the curve? The probability will be 2 steps to the right of the curve will be 0.4772. All right, from 0 to 2 steps. Okay.
If it's 0.475, that's the area under the curve, right?
That's the area under the curve. Okay. And if you see,
that would be at 1.96.
Oh,
So we would go to 0.4. Okay.
yes, yes, okay. So 1.96, you can see that, let me reduce it so that you can see it well. Okay. Oh, no. 1.96. Okay. So that will be 47.5%. That is, you are 1.96 standard deviations away to the right of the curve. You get it?
Got it.
Okay. So let's see if we can solve some problems. Okay. Let's see if we can solve some problems. How do we calculate these areas? Okay. Now, let's try to solve a problem. Let me see if I can pull up a problem for us to solve. Okay, let's look at a simple problem. So we're going to look at this problem, which we're going to solve using normal probability distribution and what we can do with it. So it says in a 1992 presidential election, Alaska's districts averaged 1,658 votes, 656.8 votes per district for Clinton. The standard deviation was 372. Find the probability that a randomly selected district had between 1,600 and 1,700 votes. Okay, now remember now that we were talking about a normal distribution, a hypothetical value called Z, and the Z has a value, a mean value of 0 and a standard deviation of 1. Now, in order to be able to solve practical problems using the normal distribution, which has a mean, which has a hypothetical variable called Z, and Z has a mean value of 0 and a standard deviation of 1. But the values we're looking at here are not 0 and 1. So in order to solve this practical problem, we have to normalize, we have to standardize these values to Z, okay? And so what we calculate are what we call Z values, okay? So what is the probability that in any particular district, the Clinton will have between 1,600 and 1,720 votes, okay? Now, if you look at this, you can see that 1,600, let me create space here. You can see that if I was to, let me draw something here. Okay, so I draw this, and you can see here that 16 58 is in the middle. Okay. 1658 is in the middle. All right. And so 1720, 1, 7, 20 is to the right of the mean. And 1600 is to the left of the mean. All right? So in order to reduce these values to Z values, we have to standardize them and say how many standard deviations away from the mean is each of these values. And remember, for the symmetrical distribution, whether you are to the left or to the right, the area under the curve is the same for each number of steps, either way, okay? If you do one step to the right, that one step to the right, the area of the curve under that step, under that number of steps is the same thing as if you take the same number of steps to the left. So we calculate V equals 1720, to be efficient, 1720 minus 1658 divided by 372. That would be the Z value. That Z value indicates how many standard deviations away from 1658 is 1720. If you calculate it, you can calculate it yourself and get that Z value. (1720) minus 1658 is 62 divided by 372. So we're looking at 1.166.
Yeah, I got the same thing.
Okay. 0.167 standard deviations away to the right. And then we calculate the next Z equals 1600 minus 1658 divided by 732. And that gives us
0.079, 0.08.
okay, over 1658. (732) 0.079.
The negative just represents the direction, right? If it's
Yeah,
on,
the negative represents the direction, but the area under the curve, whether it's negative or positive, is going to be the same.
right,
Okay,
right.
so, okay. So it's 0.079 you got, am I correct? Zero point zero seven five. Oh, 0.079. Okay. So now we're going to look at areas under the curve. Okay. I'm going to save. This is saved. So we're going to look at areas under the curve. This is a negative number. Okay. I'll stop share this, but we remember what we have, 0.167. So 0.079. So this is 0.1. Okay, we're going to use 0.17. 0.17, because 0.167. So we're going to use 0.17. And so 0.17 is 0.067. Okay, 0.675. And the other one is 0.079. So we're going to use 0.08. This is 0.0319. So 0.17 is 0.0714. And when I write it down, then I'll go back to the curve. 0.0714 and 0.0319. I'm going to stop share this. I'll go back. Okay. So what we are saying in effect is that here from 0.1658 to point zero to, I'm sorry, from 1658 to 1720, the area under the curve is 0.167 standard deviations away, which is area then is equal to 0.0714, 0.0714. And the area here is 0.0319. So the total area we are looking at is the painted area, or I would say the area that I am marking. So if you add those two areas, which is 0.0319, 0.0319, so what do you have? What you have is 0.103. Okay. That is not. Okay, it's 0.1033, which is to say there's a 10% probability that Clinton would get between 1,600 and 1,720 votes. Okay, so that is essentially how to use this. Now we're going to apply this to the next step, which is inferential statistics. And I want to stop it there so that we don't overload our head with concepts, okay? So that next time I'm going to now talk about hypothesis testing. I'm going to talk about hypothesis testing so we can take it from there and be able to solve the homework assignments. And those who feel that they have done something wrong can go and redo them, okay? And what I will prefer next time is to, like you just did, is to ask that question that you asked, those kinds of questions. But I'm going to start from um, a one sample hypothesis testing, one population hypothesis testing to a two population hypothesis testing. The question you were asking about is for a two population hypothesis testing. So I'm going to go, start with one population and then we'll go to two populations and then you can bring up your question. You understand? Hello? White, are you still there?
Yeah, Professor. Sorry. Yeah, I'm here. I'm here.
Okay. All right. So I'm going to end it here. And I'm also going to post for the class previous office hour lectures of this kind. I'm going to post them for the class so that everybody can see, can look at those and maybe use them as examples. But I will post this and I will also post the previous examples of hypothesis testing of normal distribution. You understand? Hello?
Right, Professor. Have a good night.
All right. Good night.
All right.